Welcome, everybody, to this week's very mentally stimulating new series of symposiums that are going to begin. And I thought, what better way could we launch our new series on Science Unshackled, Part 2, which will feature a lot of explorations over the coming weeks and months into the underappreciated history of science, different fruitful pathways that are highly underappreciated is not the word. I'll let people come up with their own words as we move forward throughout this little course. But certainly, science is something which, as a word, has been highly abused. Trust the science. You know, there's a lot of people who use the idea that everybody has to be proper, respectable scientists. We have to adopt a sort of consensus view of whatever some anonymous group of experts say is the way we're allowed to think and opinionate. The reality, when you look at the battle for science, is that science never moved forward because of a consensus grouping all having a common view that is managed through peer review papers, that, you know, certain things get published if it adopts or accepts certain standards or assumptions about the universe, about the nature of the mind, but rather by individuals who thought outside the box, individuals who were able to break from a sort of pattern and herd thinking in order to zero in on a paradox that couldn't be explained by the existing body of mathematical or other knowledge. And these exceptional individuals, when you really read the writings of these people, you start seeing that they're tapping into a source of honesty, of enthusiasm, of self-awareness, self-discipline that is highly underappreciated. Let's just say that again. In a very, I mean, again, I should probably find a better word in our current society. So, John Place, I'm highly indebted to Dr. Place for having introduced me to the exceptional work of Professor Andre Assis, who is a professor in Brazil at the University. Correct me, Professor Assis, it's the University Campinas. Campinas. I'm sorry.
Yes, very close to São Paulo.
Okay. And Professor Assis has done an amazing amount of work translating and popularizing the work of a very particular figure whose name I only knew in passing. I didn't properly appreciate the power and importance of this particular individual who was born in Germany in the 19th century, who did something, just many things incredible with a network of like-minded people who, again, many people who study science today do not properly value the role in the minds of these folks. So we're going to have the links to Professor Assis's works in the description box of this video. The person, of course, is Wilhelm Weber, as everyone knows, and his work on electrodynamics specifically, but a lot more will be touched upon. And Professor Assis, as usual, what we're going to do is field questions. So once you're done your formal presentation, we'll have people who can put their name in the chat box, and either myself or John Place will call upon you in as you put your name in queue. So with that, thank you so much, Professor. It is all yours.
Okay, thank you very much, Matthew. I'm sharing now my screen. Can you see it?
Yes.
Okay, so in the first place, I wish to thank the director of the Rising Tide Foundation, Matthew Ehret, and also John Place for inviting me to this talk. It's a great pleasure for me. I have been working on Weber's electrodynamics for more than 30 years, and I will share something with you. At the end, we can discuss everything you wish, okay? So I will just begin now. Usually, when we learn electromagnetism, we learn field theory based on Maxwell's equations in the middle of 19th century. The law of Gauss, no magnetic monopoles, Faraday's law of induction, and the so-called Ampere circuital law with displacement currents. They are based on the electric field E and magnetic field B. And we also have the so-called Lorentz force law. Force equals QE plus QV cross B, electric force and magnetic force. There is discussions about these concepts which we can go later on. What I will present today is a completely different paradigm, which is based on the work of the German physicist Wilhelm Weber. He was born in 1804, before Maxwell, and died in 1891, after Maxwell. He was professor of physics at Göttingen University in Germany, and he worked in close collaboration with the mathematician and the astronomer and also physicist Gauss. Gauss was the director of the observatorium, and they work in close collaboration in electrodynamics together. So in Weber's paradigm, we don't work with fields, only with the electrified particles and their mutual interactions. So what were Weber's main ideas? Weber knew Coulomb's force law, 1785, which is analogous to Newton's law of gravitation. Q1, Q2, the product of the two charges, 1 over r squared, and a central force. He also knew Ampere's force between current elements from 1822, which is also proportional to the product of the two current intensities, I1, I2, falls as 1 over r squared, and is also a central force, but it depends on 3 angles between the two current elements and between each current element and the straight lining connecting the two elements, alpha, beta, and gamma. And Weber also knew Faraday's law of induction, 1831. The electromotive force is equal to minus the mutual inductions times the time variation of current intensity. So what was Weber's main idea? No one knew what the electric current was. So Weber made an assumption. He assumed that current is charge in motion. So IDL should be analogous to QV, charge times velocity. If that is the case, in Coulomb's law, there is no velocity component. But if current is charge in motion, Ampere's force law shows that we should have a component, I1, I2, which should be V1, V2, proportional to the product of the two velocities of the charge in the currents. And if current is charge in motion, di by dt, the time variation of current, should be proportional to acceleration. So Faraday's law of induction microscopically should mean that when we change the current in the primary circuit, we induce a force in the secondary circuit. So when we accelerate charge in the primary circuit, there should be a force in the secondary circuit proportional to acceleration. So essentially, Weber said, to unify Coulomb, Ampere, and Faraday, I should introduce a component which depends on V1, V2, and a component which depends on acceleration. That was the main idea. So in slide 6, I'm showing Weber's final force law, which he presented in 1846, which is Coulomb's law, Q1, Q2 over r squared. It is a central force, but it has a velocity component, which is r dot squared over 2c squared. And r dot is dr by dt, relative velocity between the two interacting charges. And it has an acceleration component, r2 dots, which should explain Faraday's law of induction. And in this equation, Weber introduced a fundamental constant in 1846, which we call C. And it was measured for the first time by Weber himself 10 years later, in 1856. And he found its value to be 3 × 10⁸ meters per second, which is light velocity in vacuum. So before Maxwell, based on Weber's electrodynamics, people, Weber himself and Kirchhoff, they found a quantitative connection between electromagnetism and optics before Maxwell, and Maxwell knew these results. What are the main properties of Weber's force? In the static case, when dr by dt is 0 and the relative acceleration is 0, we return to the laws of Coulomb and Gauss. So the whole of electrostatic is inside Weber's electrodynamics. Weber's force follows action and reaction. Then we have conservation of linear momentum. Moreover, the force is along the straight line connecting the two charges, no matter their motion. So this means that we have conservation of angular momentum. Weber showed in 1848, 2 years later, that his force law could be deduced from a velocity-dependent potential energy, which is the Coulombian potential, Q1, Q2 over R, but it has a velocity component, R dot square over 2c square. And so he showed that if we have many particles interacting through Weber's force, the sum of the kinetic energy and the potential energy is constant in time. So there is conservation of energy with Weber's electrodynamics. So the 3 base conservation laws are valid for Weber's law. Moreover, Faraday's law of induction can also be deduced from Weber's force. You can see a proof of this fact in Maxwell's treatise. It has 2 volumes, Maxwell's treatise. The last chapter of volume 2 is wholly dedicated to Weber's electrodynamics. And Maxwell shows that Weber's electrodynamics is compatible with Faraday's law of induction. Also, the so-called Ampere circuital law can also be deduced from Weber's force. He knew Ampere and Faraday and created his force law so that it would lead to these 2 laws. And what made me, Andre, work with Weber's electrodynamics is that it depends only on the relative distance, relative velocity, and relative acceleration. This is what I call a relational force law. It depends only on R, dr by dt, and the relative acceleration. It has the same value for all observers and in all frames of reference. It depends only on magnitudes intrinsic to the system of interacting charges. It depends only on the relation between the bodies. In Lorentz force law, on the other hand, the QV cross B, that velocity, nowadays we interpret that velocity as the velocity of the charge relative to the observer or frame of reference. Nothing of this kind happens with Weber. With Weber, we have only velocities between the interacting particles. The observer does not play any role at all. This appeals to me. For this reason, I began to work with Weber 30 years ago. For those of you who wish more details, we published 30 years ago a book on Weber's electrodynamics by Kluwer. Nowadays, this book is available through Springer in Germany. So I will present only a general overview here. The Ampere's force law, which I mentioned before, is I1, I2 over R square, and it has two components, which are central forces, but depends on the angle between the two current elements, dL1, dL2, and depends on the angle between each current element and the straight line connecting the two elements. This first force law of Ampere does not appear in any textbook nowadays. We only learn in undergraduate and graduate studies the so-called Biot-Savart or Grassmann's force law, which is IDL cross B, and this B is the magnetic field of Biot-Savart, the other IDL cross R over R square. And when we open these double cross products, we end up with something similar, but not equal to Ampere's force law, which is Grassmann's force law. The bottom one is the one which we learn at school. The top one is the one which Ampere obtained, but which disappeared, was deleted. For 100 years, people deleted Ampere's force law. To show the difference between these two force laws, consider, for instance, at the top of slide 12, if we have, for instance, two current elements which are orthogonal to one another, according to Ampere, they do not exert force on one another. Force of 2 in 1 and force of 1 in 2 is 0. But according to Grassmann, the second current element will exert a vertical force in the first element, but the first element will not exert a force in the second one. So the law which we learn in the textbook does not always comply with action and reaction. Another situation is when we have two current elements which point in the same direction and along the straight line connecting them. According to Ampere, they should repel one another. According to the law that we learn in the textbook, they do not exert a force on one another. So you see, there are many differences between Biot-Savart and Grassmann on the one hand, and Ampere in the other hand. So how could we forget about Ampere and keep only Biot-Savart and Grassmann? Because there is an amazing fact. When we have two or more closed circuits, when we integrate the force of the second closed circuit acting on a current element of the first circuit, the two expressions, they agree with one another, Ampere and Grassmann. So if we have two or more closed circuits, we cannot distinguish Ampere and Grassmann. So they are equivalent for closed circuits. But nowadays, people, they are trying to make experiments with a portion of a single closed circuit. The first experiment appears in slide 14 at the top left. It was an experiment made by Ampere himself. When Ampere discovered his force law, he predicted that two current elements aligned should repel one another. So he created the so-called Ampere's bridge experiment, in which we have a bridge, and we have a mercury trough, And when we close the battery, the bridge moves forward. According to Ampere, this motion was due to a repulsion between AB, BC, which are aligned along the same line, and repulsion between EF and FG in the top left. And this would make the bridge move forward. An analogous experiment is the so-called electromagnetic impulse pendulum. A third experiment is the exploding wire, which is the figure in the bottom in slide 14. We have a capacitor bank, C, a switch, S, and a thick wire. And we have a thin wire in the middle with air gaps at the bottom. When we close the switch, we have small arcs at the two extremities, and we close the circuit electrically, but not mechanically. And the thin wire breaks into many pieces. According to Ampere's law, this should be due to this longitudinal repulsion, which does not exist according to Grassmann. According to Grassmann, the force is always orthogonal to the current element. So nowadays, many experiments brought back Ampere's force law once more. So people are doing experiments with a single circuit, not with two or more closed circuits, but with a single circuit in which a portion of the circuit is mobile, like in Ampere's bridge, or in which a portion of the circuit can break or can explode and so on. So these experiments brought back Ampere's force law. It is amazing that Maxwell himself, he knew not only the so-called Biot-Savart and Grassmann's force law, but he knew also Ampere's force law. And in his treatise on electricity and magnetism of 1873, he compared 4 different force laws between current elements. That of Ampere, 1826, that of Grassmann, 1845, and 2 others which Maxwell himself created. And Maxwell made the following, said the following: of these 4 different assumptions, that of Ampere is undoubtedly the best, since it is the only one which makes the forces on the 2 elements not only equal and opposite, but in the straight line which joins them. In the next paragraph, Maxwell made the following assessment of Ampere's work in the treatise: the experimental investigation by which Ampere established the laws of the mechanical action between electric currents is one of the most brilliant achievements in science. The whole theory and experiment seems as if it had leaped, full-grown and full-armed, from the brain of the Newton of electricity. It is perfect in form and unassailable in accuracy, and it is summed up in a formula from which all the phenomena may be deduced, and which must always remain the cardinal formula of electrodynamics. This was Maxwell. But you see, nowadays, this expression of Ampere at the top of slide 11 disappeared from every textbook. Also, Maxwell said that it should always remain the most important formula of electrodynamics. It disappeared. Why? Because it is incompatible with Lorentz force law. With Lorentz, we arrive only at Biot-Savart and Grassmann. As relativity is based not only on Maxwell's equations, but also on Lorentz, the textbook writers decided to delete Ampere and keep only Grassmann. But this was against the opinion of Maxwell himself. Maxwell knew all these two formulas and said that Ampere is best, and it should always remain the most important formula. This was Maxwell, okay? Now, for those of you who wish to see Ampere's own works, we published a few years ago English translation of Ampere's main book on electrodynamics, Theory of Electrodynamic Phenomena, Uniquely Deduced from Experience. This book had never been translated into English for 200 years. What we call Ampere's circuital law was never written down by Ampere himself. Ampere didn't work with the magnetic field concept. He never wrote down the circuital law, which appears in every textbooks under the name of Ampere. What Ampere obtained was a force law, which does not appear in the textbooks. But nowadays, everyone can read Ampere's original text, not only in French, but also in English translation, a complete translation of his book. You can download this book from my homepage and read that later on. I will now change subject. People usually think that the wave equation was only obtained by Maxwell, but the first time by Maxwell. But this is not at all the case. The propagation of electromagnetic signals was first obtained by Weber and Kirchhoff 7 years before Maxwell, in 1857, utilizing Weber's electrodynamics. In particular, they obtained the Telegraph equation, both of them working with Weber's electrodynamics. I won't go into the details here, but in slide 19, at the bottom, we have the so-called Telegraph equation, which is a wave equation, a signal propagating along a wire, and it has at the right side, if the wire has resistance, so the signal will have an exponential decay in its magnitude. This was obtained by Weber and Kirchhoff, the same of Kirchhoff's law of circuits, the first and second Kirchhoff's law. And this was obtained before Maxwell, 7 years before. So what we have in the textbooks? In the textbooks, we read in every textbook, Jackson, Feynman, Griffiths, and so on, that Maxwell introduced this displacement current in Ampere's circuital law. Ampere's circuital law should be the rotational of the magnetic field is proportional to the current density, J. But then Maxwell saw that this equation was not compatible with conservation of charge, and then he introduced the so-called displacement current. This is what appears in the textbooks. However, what the textbooks, they don't mention is the C, which appears in the displacement current, had been introduced by Weber in 1846 in his force law. Maxwell also knew that the first measurement of this constant C was made by Weber himself 10 years later in 1856. And Maxwell also knew that Weber and Kirchhoff had obtained the wave equation in 1857. So when Maxwell obtained the wave equation with his displacement current, he utilized Weber's constant, knew the magnitude of this constant, and knew that Weber had obtained before the wave equation. So what Maxwell made was nothing new. Also, this does not appear in any textbook, okay? But these are historical facts. Also, the textbook, they don't know. It is historical facts, published results years before Maxwell. What are the main differences between the forces of Weber and Lorentz? The force of Weber depends on the position, velocity, and acceleration of the two interacting charges, 1 and 2. Lorentz force, on the other hand, depends only on the position and velocity of the test charge, but it does not depend on the acceleration of the test charge. In Lorentz force, QE plus QV cross B, there is no third component, QA1 times S or any other field. There is no component in Lorentz force which depends on the acceleration of the test charge. But with Weber's law, we have this component. And I will show you some differences, different predictions between Weber and Lorentz. The first situation, suppose that we have a spherical charge, a charged spherical shell, and the shell is uniformly charged with a charge capital Q. And inside the spherical shell, we have a particle, an electron, for instance, and we accelerate the electron. What is the force exerted by the shell on the internal test particle? According to Lorentz, the force is 0, because the spherical shell does not produce inside it electric field nor magnetic field. But according to Weber's force, if you accelerate the test charge relative to the shell will exert a force on the internal test charge, which will depend on the acceleration of the test charge relative to the shell. So if we combine this result with Newton's second law of motion, F equals ma, so we can pass this component of Weber to the right-hand side, and the electron will behave as if it had an effective inertial mass, okay? Because its inertial mass will depend. It will depend on the electrostatic potential of the shell around the test particle. So this is one very important difference that we can try to test experimentally. And what happens when we rotate the spherical shell? When we rotate the spherical shell, according to classical electrodynamics, it will generate inside itself a uniform magnetic field. Outside, it will be a dipole field. But inside the shell, the magnetic field will be uniform, pointing along the direction of the axis of rotation. So in this case, there will be Lorentz force law, QV cross B. And what will be the force in this case according to Weber? According to Weber, we will have three components. The previous Q1, Q2 over 12 pi r A, which was the previous one. But there will be an omega times r, which is analogous to a centrifugal force. But in this case, it is an electrical centrifugal force. And it has a 2v times omega, which, if you remember mechanics, this is like a Coriolis force. And this Coriolis force will be equal to the magnetic force of Lorentz, QV cross B. because we have a 2 in the numerator, 12 in the denominator. We will have 1/6, just like the magnetic component of Lorentz force law. But there is no centrifugal component in classical electrodynamics, but there should be according to Weber. So again, we can try to make a test, experimental test of these different predictions, okay? So these previews at the bottom of slide 25, if we suppose instead of charges, if we apply the same law for gravitation, like a Weberian force for gravitation, so we will have here the centrifugal and Coriolis forces of mechanics. So this is the essence of the relational mechanics. That is, if we apply Weber's law for gravitation, we can obtain a mathematical implementation of Mach's principle with Weber's gravitational force. I won't go into the details here. For those of you who wish to give a look at that later on, this book on relational mechanics is available in my homepage. So you can see that later on. But it is just fascinating that if you apply Weber's law for gravitation, you can obtain a mathematical implementation of Mach's principle, that the inertia of any body is due to its interaction with the distant galaxies in the universe. You can explain Newton's bucket experiment, the flattening of the Earth, Foucault's pendulum experiment, and so on, based on relational theory, relational mechanics, which is completely different from Einstein's theories of relativity. It's another theory, another paradigm. What I will present now to you very briefly is Weber's planetary model of the atom, which is just fascinating, which was developed by Weber in 1870s and 1880s, at the end of the 19th century. So let us consider an interaction of two charges, F equals ma, Newton's second law of motion. But the force now is Weber's force, which at the top of slide 27 is Q1, Q2 over R square, parentheses, 1 minus R dot square over 2 C square plus R2 dots over C square. If the velocity is small compared to light velocity, we can forget about the middle term. And the acceleration component, it is just like ma, but in this case it is Q1, Q2 over 4 pi epsilon naught r, the distance between the charge, c square. This last component, we can pass it to the right-hand side. So we will end up at the second equation in slide 27, which is Coulomb's force equals, parenthesis, mass minus Q1, Q2 over 4 pi epsilon naught r over c square. So this is like Newton's second law of motion, but now with an effective inertial mass. We can ask when this effective inertial mass will go to 0. So m equals Q1, Q2 over 4 pi epsilon naught r c square. So we obtain a critical distance when the effective mass goes to 0, which is Q1, Q2 over 4 pi epsilon naught mc square. So this is algebraic expression. Now let us plug in numbers. Weber didn't know about the electron and positron at the 19th century, But suppose we have two positrons. Let us calculate when two positrons will begin to attract one another, or when the effective mass of each one of them goes to zero. So we will put Q1 equals to Q2 equals to the charge of the electron or the positron. And the mass will be the mass of the electron or positron. When we plug in the numbers, we obtain 10 to minus 15 meters, which is just fascinating. For distance greater than 10 to minus 15 meters, the charge will repel one another as usual. But for distance smaller than 10 to minus 15 meters, two positrons will behave as if they had negative inertial mass. So instead of repelling, they will attract one another. So at the end of the 19th century, Weber predicted in his mind and in his papers that the atom should be composed of a positive nucleus and negative particles describing elliptical orbits around the nucleus. And the nucleus would be held together by Weber's force law. And the nucleus would have a size which he couldn't calculate the numbers, but now we can. So with a bunch of positrons, the nucleus would have a size of 10 to minus 15 meters. So this is Weber's planetary model of the atom, which is just fantastic. Why? What are the predictions of Weber's model of the atom? In the first place, it was a real prediction, 1870, 1808. It was made before the discovery of the electron, 1897, by Thomson, before Balmer's spectral line series, 1897, before Rutherford scattering experiments, 1911. Bohr's model, on the other hand, is from 1913. He knew electron, he knew the Balmer's spectral series, and he knew the Rutherford experiment. So he created his planetary model to be compatible with these results. But Weber was much more fantastic because he predicted before all of these experiments. Moreover, he couldn't calculate when the two charges would attract one another because he didn't know the electron and the positron. But when we utilize the modern values of the mass and charge of two positrons and plug in Weber's formula, which he calculated in the 1870s, we obtain that two positrons will attract one another for distance is smaller than 10 to minus 15 meters, which we know nowadays that is the right size of the nucleus. So Weber's model gives an explanation why the nucleus has a size of 10 to minus 15 meters. So in modern physics, we need to postulate the existence of nuclear forces to explain the stability of the nuclei, because it should explode due to Coulomb. We have many positive charges together inside the nucleus. It should explode, but it doesn't. So people postulate that you have an opposite force, which they call a nuclear force. But with Weber, we don't need that, because the nucleus is held together by Weber's electrodynamic force law. So we can forget about the nuclear force because we have already an unification before a separation of these two branches, because people forgot about Weber's electrodynamics. If they had continued with Weber, we would didn't need the nuclear forces. because everything is electrodynamic. It was predicted by Weber. It's so fantastic. It was published. It is history of science. It is there, published before the end of the 19th century. All of these results were published and then forgotten. Has been forgotten for 100 years, but they were published there. Okay? Also, it was forgotten. For those of you who want to see more details about these, we published 2011, myself, the Carl Wiederkehr, which was the main biographer of Weber. I worked with them, and Gudrun Wolfschmidt, an astronomer. I worked with them in Germany, and we published a book on Weber's planetary model of the atom in English, so you can read about that later on if you wish. I could discuss here about superconductivity, but I will skip that for the moment. If you wish, we come back with this. I published a paper with Professor Teimar of Dresden. We can deduce the Meissner effect, the London penetration depth, the London moment. With Weber's original force law, we don't need any free parameters or nothing, just Weber's 150 years old. When we apply it to superconducting materials, we deduce the Meissner effects and so on and so on. I won't go into details here. Those of you who wish, you can read the papers and so on. Last year, we published 4 volumes with the English translation of Weber's main works on electrodynamics. So we have 4 volumes. I did edit these 4 volumes, but there were many colleagues of mine in the USA, in Germany, in Austria, who helped me to make these translations. 99% of Weber had never been translated into English. So it was very important at the 19th century, but when we did change the paradigm, so it was completely forgotten very quickly. In the beginning of the 20th century, had already been forgotten, disappeared from the textbooks. But now the 4 volumes, his 8 most important memoirs on electrodynamics are now available, not only in original German, but also all of them complete commented translations into English. These 4 volumes, they are available in my homepage if you wish to give a look later on. So, conclusion, Weber's electrodynamics is extremely powerful. We have conservation of linear momentum, angular momentum, energy. We deduce the laws of Coulomb, Gauss, Faraday, Ampere, the wave equation, telegraph equation, Meissner effect. If we apply that to gravitation, we have Mach's principle, Newton's bucket, Foucault's pendulum, flattening of the Earth, and so on, precession of the perihelion, and so on. In the last few years, there has been a renewed interest in Weber's electrodynamics due to novel experiments and theoretical developments. So thank you for your attention, and we can discuss as long as you wish. Thank you once more, Matthew, for the invitation, and John Place.
Thank you, Professor Assis. That was an incredible introduction. Just as you were speaking, I took the liberty to go online and purchase about 10 of your translations, and I was pleasantly surprised at how affordable they are. And in my experience, usually when I try to look for original translations of the original works of great thinkers, they're very prohibitively expensive. These are
I have one of these volumes here, for instance, this one here, which is volume 2, and this is Weber at his height, his peak. This one, for instance, has 460 pages, volume 2. I believe it should be $5 or so.
I paid $10 Canadian. Yeah, that's right.
Okay, so they are all very cheap, and they are also free. All of them, they are in my homepage. And by coincidence, the Rising Tide Foundation is located in Montreal, I believe, in Canada. Yes. And this publisher, Apeiron, is also of Montreal in Canada. So,
his name is Roy
many
Keyes.
of my books, they are from your neighbor, Matthew.
All right, I'll knock on their door. What was that, John? You were gonna say something?
His name is C. Roy Keyes. He lives in Plateau.
Oh, wow. Yes. I had no idea. That's okay. We have to have a coffee. Well, I got the first question I'm going to just sneak in there, Professor. If you were, it's sort of a big question that touches on the what you said at the very end regarding the fallacy of the strong nuclear force as being sort of an unnecessary creation that is not necessary in the Weber electrodynamics. If you were to advise, if you had the clout to advise a science policy on the development of fusion power, what sort of pathways would you encourage scientists and those who might have the influence to give the means to build prototypes, build and test out ideas? What type of pathways would you suggest would bear a lot of fruit that would be unencumbered by the presumption of the strong forces that are, justifying pouring a lot of money into tokamaks and particle accelerators and things? So what would you say?
Go ahead with Weber directly, because you see, my own my own field of research, my PhD was in plasma physics. And then I went for 1 year in England at the Culham Laboratory in Oxford, and they have the Joint European Torus Jet and so on. People have been working, trying to obtain controlled nuclear fusion for 70 years now, since the 1950s or so, with, as you said, tokamaks and things like that, without success. My own opinion is that we didn't obtain this goal because we are following the path which everyone learns at school, which is based on Faraday, Maxwell, and field theory, and Lorentz force law. But I believe that if we go with Weber, and Weber's electrodynamics, his force law, which he showed the stability of the nuclei, that it's essentially only electrodynamics. We don't need, as you said, nuclear force and so on. Then we can also make the opposite, begin with electrodynamics and obtain what we call nuclear energy out of it, but in a controlled way. But we need more people to work on this theory, which has been completely forgotten. People nowadays, they only know Weber because it appears in a footnote in electrodynamic textbooks about the units of the flux, magnetic flux. It's so many Gauss or so many Webers. They just give a footnote, but nothing about Weber's force law and so on. But Maxwell knew everything about Weber. If you read Maxwell's treatise, the person who Maxwell quotes the most beyond Faraday is Weber. And he praises Weber highly, highly, because of the precision of Weber and Gauss measurements. The whole CGS system of units is based on Weber and Gauss absolute system of units on 3 basic units, mechanical units. So Weber always praised highly Weber. But nowadays people, they don't read more about history of science. So Weber was completely forgotten. And even Ampere, Matthew, it is amazing because every textbook calls Ampere circuital law, line integral of the magnetic field equals to the proportional to the current which crosses the circuit. Ampere never wrote such an equation, even without displacement current. Ampere, moreover, if we have a current here, Ampere, we say, oh, we have a magnetic field by the right-hand side. It circulates around the current. Ampere did fight against this idea, Matthew. He did fight against, he never worked with a magnetic field. he fought against Ørsted, against Faraday, against Biot, because all of them believed there was something circulating around the current. Ampere said, no, there is nothing. We have only central forces of Newtonian type. So every textbook is wrong, but one copies from the other, copies from the other, from the other, from the other, and no one goes to the original. Ampere was never translated into English.
Wow.
It is just amazing, crazy. What they call Ampere, Ampere himself fought against these, against anything circulating around the current carrying wire. He begins the first paragraph of his main book. He's fighting against Ørsted because Ørsted believed there was something circulating around the current carrying wire. And Ampere said, no, we don't have vortices. We don't have anything of this kind. We should have Newtonian central forces. But his force law disappeared. And what they call Ampere is a misnomer. Ampere never wrote that. It's just crazy. But it is a pity, but it is how we learn science nowadays.
Sub question based on that, and then I'm going to let John throw some questions at you. But would you say that Ørsted's work combining or discovering the connection between electricity and magnetism, was that valid, or was that something?
Yes, that's completely
still
valid.
Okay.
And his result that if you have a current and a magnet, it deflects and so on. But in order to explain that, so Ørsted believed that inside a current we have charge moving in opposite direction. And he said, outside the current, there is a spiral of charge moving outside the current. And this charge is moving around the current will interact with the magnetic poles. It is his explanation. The effect is there, but in his explanation, he assumed a force between a charge and the magnetic pole, and and Ampere also fought against these because he said, no, we need to have interactions of two kinds of the same type. So for this reason, Ampere said it must be interaction between current and current, interaction between current elements. And so Ampere said, inside a magnet, we must have currents spinning there. And in the wire, so we don't have an interaction between a current and a magnet. What we have, in fact, is interaction between current in the wire and current in the magnet. So this was the beginning of the Amperian idea of the unification, that magnets are made on molecular currents and so on.
Okay, thank you. John.
Thank you very much for the wonderful presentation. I've been following your work for a number of years. I'm not a professional physicist, but I am very much interested in this. In fact, I remember us corresponding was a few years ago when you were starting to organize the translation project of Wilhelm Weber. I think implicit in everything that you're doing is the idea of action at a distance is implicit in all of the equations that you're manipulating, whether they're Isaac Newton's, Charles-Augustin de Coulomb's, André-Marie Ampere's, or Wilhelm Weber's. And yet, when Newton was presenting his Principia, he was criticized quite overtly by Gottfried Leibniz because he was introducing the occult.
Yes.
So do you have any idea on how Leibniz's criticism could be reconciled with Weber's work?
Well, you see, when we obtain these, let me go back here. when in slide 25, we see a force of a spinning shell on a particle inside. We have these three components, A, omega times R, and 2V times omega. In mechanics, we recognize that as MA of Newton's second law, the centrifugal force, which is the middle one, and the right one is the so-called Coriolis force. These are forces that we need to apply on the Earth, in the frame of the Earth, in order to explain the precession of the Foucault's pendulum and so on. So if we apply Weber's law for gravitation, we obtain an implementation of Machian ideas, of Mach's principle. And Mach's principle, they are just based on Leibnizian ideas. They are very similar. The ideas of Ernst Mach, Leibniz, and Berkeley. So in a way, we have these, John, that with Weber's law applied to gravitation, we go back to this idea of Leibniz, Berkeley, and Mach, that we have only relative motions. That is a fantastic, to me, that's just fascinating. We can go to discuss this here if you wish, but I don't know if that would be too much specific, but you are right. You are, so in a way, we can go back to Leibnizian ideas with Weber. And that is the essence of the mathematical implementation of Mach's ideas. We just need to apply, instead of Newton's law of gravitation, we say that the force between two masses also depends on relative velocity and relative acceleration. Then we deduce Newton's second law of motion, MA. We don't need to begin with that. We deduce the Newton's second law of motion.
Important. That's very important.
That is, to me, that is just amazing, so fascinating, because then we complete the whole circle. You see, you went to the cairn point, to the crucial point, John.
Thank you. I have a second question. Is it possible to do computer simulations with the Weber model?
Yes, sure.
Because when I think of Maxwell's equations, there's a lot of computer simulations that are particle and cell, where you just look at the movement of the particles, you move the particles, and then you update the magnetic and electrical fields, and then you do the next step, and you repeat this over and over.
Yes, sure you can. And not only that, it's much simpler than with Maxwell's equations, because Weber is so simple. The potential energy is just a scalar quantity. And if you have, this is the potential of Weber in slide 7, and the Weber's force in slide 6 is a central force. So it's ordinary differential equation of second order. It's not even partial. So it's much simpler than with Maxwell. But people, they don't do, because they don't learn it any longer. But nowadays it should be so simple if you apply Mathematica or any other software to apply it with Weber. For people who work with computers, that should be so simple. Let's do it, young people, young physicists and mathematicians who are hearing me. Just begin, play with that. Even if you don't believe, just begin and play, see what you get. You see how simple it is, because it is ordinary differential equation of second order. It's not even partial. It is just crazy.
So my last comment is, there's a man named Peter Watson who wrote many years for the London Times and the London Sunday Times. And he wrote a book called The German Genius, which essentially starts after Leibniz and talks about all sorts of wonderful things about Schiller and Goethe. And when it comes to Wilhelm Weber, he simply states that he was a very skilled experimentalist. And he completely leaves out the entire tradition of theory. I mean, Weber was the thesis advisor for, Weber literally taught the physics to Wilhelm Riemann. I mean,
yes, yes. Riemann was his student, and
yeah,
Riemann
so
did participate in some of the experiments with Weber and so on. And so Riemann was his student, and also a student of Gauss, of course, but also directly of Weber when he did some experiments. But you see, all this tradition disappeared. Maxwell is fascinating because Maxwell, in the introduction of his treatise, he talks about the German tradition, and he says, okay, there is essentially Gauss and Weber and Neumann, Karl Neumann and Franz Neumann, his father, and Kirchhoff and Riemann and so on. He calls it the German tradition. But Maxwell says, I won't be a judge. I will be a lawyer of the side of Faraday. And he goes on. But Maxwell is very fair and very praises highly all of these German tradition. And he knew everything about this tradition. But soon after Hertz, it's essentially because Helmholtz was against Weber, and so on and so on. So after Hertz experiment and Lorentz force law, and especially because relativity was based not only on Maxwell's equation, but in Lorentz force law, and due to the success of Einstein's theories, they deleted completely all this German tradition from the textbooks for the end of the 19th century. For 130 years now, 40 years, 140 years, disappeared completely from the textbooks, this paradigm. And also Maxwell talked many places about Weber, highly praising Weber. But at the beginning of the century, in every textbook was only based on Faraday and Maxwell and Lorentz and relativity. And so everything which was against, for instance, this Ampere's force law, because with Lorentz, in slide 11, with Lorentz we deduce only Biot-Savart and Grassmann. With Weber we deduce Ampere. You cannot deduce Ampere from Lorentz. So people, textbooks, ignored Ampere completely. Also Maxwell said that the Ampere force should always remain the most important formula of electrodynamics. It disappeared from all textbooks since the beginning of the 20th century. It was in the beginning, I believe it was with intention. Later on, the others just copy from one another, and the reason was forgotten. But the fact is, Ampere disappeared, and Weber. And what they did call Ampere was never written by Ampere himself. And so Kepler, this tradition was lost. This German tradition was lost.
And Kepler has also mostly been disappeared as well. But
yes, yes. The same. Kepler was also never translated. Only in recent times, his works are being translated. The same.
Yeah.
Mm-hmm. Ampere himself never translated. Coulomb was never translated. The French and German traditions were ignored. They even mentioned their names, Coulomb and Ampere, but many times with wrong connections, like Ampere circuital law, which is a complete misnomer, which Ampere would fight in his grave against this, and never he would hear about this Ampere circuital law, because in the first paragraph, he's fighting against anything circulating against a current carrying wire. He follows the Newtonian tradition. He would certainly be for 200 years fighting in his grave against every textbook, but he's no longer alive. So, but now finally we have English translation of Ampere, Coulomb, and Weber. So I hope this tradition will come back to light again. If you help me, all of you.
Yes, absolutely.
I have more questions, but I'll let others ask them before I maybe ask a final thing.
And yeah, just so people are aware, Professor Assis has translated Coulomb's work as well as Ampere's work, and all of these things are among the books that are available for, again, very affordable prices online.
Amazon.
So, and
Amazon, yes.
Yep. Yeah, there's a couple of questions I have, but I know other people are waiting, so I'll withhold as well for now. No, I won't. Wait a minute, I'm a moderator. I can ask a question whenever I want. Okay, since you just brought up Kepler and Leibniz, just quick, there's two interconnected, underappreciated concepts that emerged in that body of work, and I'm curious about Weber's. When you've been working through Weber, the idea of the harmonic orbiting of the planets around the sun, so harmonics of Kepler's work, as well as the concept of least action pathways that Leibniz also developed, that obviously play a very interesting lawful role within the system of the planetary model of Kepler, that there's these harmonic least action pathways that are the orbits that we find in the elliptical functions. Did you encounter in Weber's work a sensitivity or remarks, a thinking, whether he's working on the planetary orbit of the atom or other places, an idea of harmonics and the Leibnizian idea of least action pathways?
Not specifically least action in Weber, but Weber, you see, it's fascinating. Weber obtained that his force is like Coulomb, but with small corrections. And Weber could show that there would be precession of the perihelion, which is fascinating, that later on we found by Mercury and so on. But Weber found that for charges. But if we apply Weber for gravitation, then we obtain the precession of the perihelion as well. But you see, the son of Franz Neumann, the Carl Neumann was a mathematician, and he was on the side of Weber against Helmholtz. And Carl Neumann was the person who introduced the Weberian, Hamiltonian, and Lagrangian, which are related to this minimum principle and so on. So and in this collection of 4 volumes of Weber's work, there is a translation of the paper by Carl Neumann, in which he introduced the Lagrangian and Hamiltonian of Weber's electrodynamics. So it is there as well. But it was made by the son of Franz Neumann. Franz Neumann introduced the self-induction and so on, and his son, he did fight together with Weber against Helmholtz and against Kelvin. In Germany, the main opponent of Weber was Helmholtz, and later on his student Hertz and so on. And in the UK, in England, the main opponents were Kelvin, Lord Kelvin, and Tate, P.J. Tate. They did even said that in one of their books that Weber's theory was very dangerous, because it not only leads to Ampere, Faraday, and so on, but it conserves linear momentum, angular momentum, and energy. Because in the beginning, Helmholtz said that Weber should not conserve energy. For many years, there was a discussion. But when Weber finally convinced everyone, specifically Maxwell, that his force law conserves energy, then Lord Kelvin published a book saying that it's a very dangerous theory because it is too good.
Wow.
But you see, and it was Helmholtz and Kelvin, specifically, these two guys, who in the International Congress, first International Congress for the naming of the units in 1881 in Paris, the unit of current would be named Weber, because Weber created the electrodynamometer to measure currents. He made measurements of current by the electromagnetic, by the amount in which you deflect a magnet, by the amount of molecules that you decompose in water by the amount of charge which crosses the cross-section and so on. So they would name the unit of current would receive the name Weber. But in this Congress, Weber was not there. Maxwell was already dead. He died in 1879. And so when this first Congress met in Paris in 1881, they did meet in a cafe. There is a report of this in the French edition of this Congress, right, by the French guy who was responsible for this Congress. And they met in a cafe and they crossed Weber and put the name Ampere in its place. So they were the responsible for removing the name Weber from the units. Only in 1926, after many years, they saw the great injustice they did make with Gauss and Weber, who created essentially the CGS system, which they call the absolute system. And so in 1926, they gave the name of Gauss and Weber to the magnetic flux. But it was Kelvin and Helmholtz, the main opponents of Weber, and the main responsibles for forgetting about this German tradition.
Huh. Extraordinary. We have a few people waiting, so let's get on to Stephen, who's been waiting for a long time. Stephen Doyle, are you still there?
I am. Thanks, Matt. Professor, thanks so much for a great lecture. My knowledge of physics is very humble, so you have to bear with me. But when you've talked about how Ampere's work varies from Grassmann's and Weber from Lorentz and all that sort of stuff, I believe that also applies from Maxwell's original equations in quaternion form to the current vector form that Heaviside changed. How would Weber's work influence your interpretation of Maxwell if you were looking at it from the original quaternion interpretation? And just as an added question, would that in any way argue for the return of Aether into the conversation in physics?
Well, as regards the first question, I don't know how to answer, because I don't know this tradition of I know that in the treatise, Maxwell himself, he presents his equations in the quaternion formulation of Hamilton and so on. And later on, as you said, Heaviside did change that, and but I don't know if that would change. As regards the ether, not only Maxwell did believe in the ether, but Weber himself did believe in the ether. Both of them, they did believe. The difference is that to Maxwell and Faraday, the ether was more or less a continuum, a field continuum or a continuum of matter and so on. To Weber, it was like a gas of electrified particles. So it was a granular or discrete gas, like a plasma, a gas of electrified particles. And moreover, the interaction between any two particles would be instantaneous. You might have a wave propagating, but the interaction between any two particles would be instantaneous. But out of that instantaneous and the many-body problem, Weber was the first to deduce a wave equation propagating, either in a wire or maybe it might, he believed that it might also be the case for wave propagating this medium, this ether.
Oh, interesting. And a very quick follow-on question. If we think of torsion physics from, I believe it's Mishkin, Eli Carter, and Kozyrev, to me, that would relate to your slide 25 with the rotating sphere. Has anyone looked at Weber's original equations in this context and thought about it in terms of the torsion physics, the Russians, and Kozyrev, and to see if there's any relation or deeper insights that be gained?
I believe that might be a relation, but I don't know any work in this connection, because as I said, for essentially 130 years, this complete tradition was completely absent from the textbooks and from the mind of the scientists, students, engineers and physicists, because they don't learn it. So everything should be done again from scratch, almost, because it was a tradition which was interrupted. So it needs to begin again. So especially young students and mathematicians, physicists, engineers, with the very powerful tools we have nowadays, computers, simulations, and also experiments. So we can do so many important things, but we need to begin again. So I hope that you will help me to bring this to the attention of the young generation. Really, really hope so. And any one person that you can bring the attention, you have no idea how important that can be. Even for one person, because this person can be important, can reach others and others and others. This is a whole tradition which was interrupted at the end of the 19th century for 130 years now.
Thank you very much, Professor. Appreciate that.
I think your remarks, Professor, sort of opened the door to a question that Hugh Trudeau in Ottawa is holding in mind. Hugh, are you still there?
I'm still here, but I'm invisible. I think my camera's not working.
We can hear you.
Wonderful, very interesting stuff. I'm really not a scientific type of person, but you did say something, Professor, about that. I mean, I can understand all this kind of happening on the subatomic level, but you seem to say things that related it to the quasi-galactic level.
Yes.
And that, I mean, I was just reading a few other things about, the galaxies all seem to be rotating in the same way in a similar pole. But I know nothing about it. Could you elaborate a little bit on how this would work at a macro level, if you like?
Yes. I think this is a very interesting question, because we have the flat rotation curves of galaxies that if we see the solar system and so on, and if we apply Newtonian gravitation, the Keplerian, the laws of Kepler, they do not apply at the distance of the size of a galaxy. So I believe there is a possibility of obtaining this kind of thing when we apply Weber's law, for instance, in slide 22. Because if we apply that for gravitation, we will have M1, M2 instead of Q1, Q2. So the first component would be Newton's law of gravitation. The second component would be velocity component, which for gravitation we can forget because the velocities are very small. But the last component, which in electrodynamics leads to Faraday's law of induction, you see we have an R in the numerator and an R square in the denominator. So this last component follows as 1 over R. So if we have this 1 over R, so when the distance begins to be very great, this last component can dominate relative to the Newtonian component. So this might explain these flat rotation curves of galaxies. I don't know if it will explain or not, but you see there is a possibility here. Because if the forces were 1 over R instead of 1 over R square, then we would have these flat rotation curves of galaxies. But you see, we need to apply it. So, in this book, Relational Mechanics, we have examples of application of Weber's law for gravitation. And I bring, for those of you who never read about relational mechanics, I bring to your attention a very important paper by Schrodinger, the father of quantum mechanics. I believe it was maybe his very last paper before the wave equations, which was in 1925. he begins a paper saying that we know that general relativity does not implement Mach's ideas about the origin of inertia. And Schrodinger was in Vienna, and he was very influenced by the ideas of Boltzmann on one side and Ernst Mach in the other side. And he wanted to implement the Machian ideas. Mach was very powerful. And so, but he knew that with relativity, Einstein general theory, we cannot obtain only a partial implementation of Machian ideas, but not a full implementations. So in this paper, 1925, before the 3 papers on the wave equation, he did apply a Weberian potential, just like in the beginning here, in slide 7. So this is the Weberian potential, Q1, Q2 over R, parentheses, 1 minus R dot square over 2C square. So Schrodinger says that heuristically, if we want to implement Machian ideas, the kinetic energy, every energy we have is an interaction energy. Q1, Q2 over R, interaction between 2 charges. The potential energy of a spring, Kx squared over 2. Every energy is interaction of bodies, except the kinetic energy, which is an energy of pure motion. So Schrodinger says, if we want to deduce the kinetic energy following the ideas of Mach, then we need to have a component, just like slide 7 here, but with gravitation, m1, m2 over R, which is the Newtonian potential energy. And Schrodinger says that heuristically, I will put R dot square over C square. And then he integrates that for a spherical shell, a body inside a spherical shell, and he obtains the kinetic energy as an interaction between this particle and the shell. The shell here would represent the remainder of the universe.
Oh.
Okay, stars around anybody. For instance, this pen here is surrounded not only by these walls, but by stars and galaxies all around this pen. So if I move this pen like that, it is moving relative to the environment. And Schrodinger, when he integrates this Weberian potential, he obtains a kinetic energy. But the most, so it is a mathematical implementation of Mach's principle here, Trudeau. And I'm trying to answer your, somehow, to bring something to your attention.
Yes.
But the most amazing thing is that Schrodinger is publishing in German, in the Annalen der Physik, where Weber published most of his papers. And Schrodinger never mentions the word Weber. He says that he created that potential heuristically, which means by trial and error. But then, if you go to the correspondence of Schrodinger, there is another guy, Heisner, who wrote to Schrodinger when he saw this paper, 1925, and said, Schrodinger, you are copying my paper, because Heisner, published a paper in 1917 with this potential. And then there is a reply by Schrodinger to Heisner. And he says, oh, I apologize, Heisner. It was during the war, and Heisner had published 2 papers, one in 1911, I believe, and one in 1917. And Heisner and Schrodinger says, I saw your first paper. I didn't mention you. And the second one, I'm not sure, because it was during the First World War. But then he underlines this potential belongs to Heisner. You see, Schrodinger and Heisner, they were publishing in German, 1911, 1917, 1925, and no one knew that this potential does not belong to any of them. It belongs to Weber.
That's because
75 years before. 75 years before. And
Wow.
This potential appears in Maxwell's treatise, but no one read Maxwell's any longer. You see, it's amazing, but the history of science, what I meant, it was completely deleted. Even the German-speaking people, like Schrodinger, he didn't learn nothing about Weber. And this paper by Schrodinger in particular has just been translated into English. I was in a conference in Germany in 1994, I don't remember. The book is called Newton's Bucket from Mach's Principle, from Newton's Bucket to Quantum Gravity, organized by Julian Barbour of England and Pfister of Germany. And there they have an English translation of this paper by Schrodinger of the Annalen der Physik. You can read there. And you see that he says that he arrived at this potential heuristically. The exchange of letter is not in this book, but they mention that in this book. And you can read this exchange of letters between Schrodinger and Heisner in the collected works of Schrodinger. But you see, Weber was already buried, forgotten in 1925.
So on the basis of that, I can deduce that by changing some of the variables, yes, you can extend this theory or practice out to the quasi-galactic. And two, that physicists are, like everybody else, sometimes jealous professionals.
Yes, I know. I know from first-hand experience.
For sure.
Kevin has a question about the structured atomic model. Kevin, are you still there?
Yep. So can you hear me?
Yes, sir.
Yes.
All right. So, well, first of all, thank you, Professor, for this exposition of Weber. I've never heard of him before, as you said, which is, I guess, historically normal.
Yes.
I'm still trying
99.9% never heard of
never
Weber.
heard of it.
Just that footnote that so many Gauss or so many Weber as flux units.
Right, but well, I gotta say, you definitely got me intrigued. So I'm still trying to collect my thought a little bit. I have to revisit this talk for sure. But my question is, well, first of all, are you aware of the structured atomic model? Yes. Okay.
Yes.
So because from one of the things that I gathered from Weber's force law, and especially when you were talking about the unnecessary existence of the weak nuclear force and the strong nuclear force at when you have a 10 to the minus 15 meter distance. Do I understand correctly that to get this result, the two particles in consideration have to be in constant motion, meaning that R dot and R dot dot cannot be zero, basically, right?
Exactly.
Okay.
And not only that, they cannot be, it cannot be, for instance, a circular motion, because then R would be constant, R dot 0 and R2 dot 0. They must have like moving like that. There must be some kind of acceleration. It must be dynamic.
But so, it has to be some kind of, there has to be a frequency in the radial movement between the two particles, right?
Yes, yes. And okay. Weber himself even calculated this frequency and so on and so on.
Okay. So,
but it doesn't need to be a specific, you can have many kinds of motion.
Sure. But it has to be in motion.
If they are accelerated relative to one another, and if the distance is smaller than 10 to minus 15, they will be attracting one another, behaving as if they were attracting one another, and they will remain inside this distance.
Okay, so my question regarding the structured atomic model, and maybe I know John, you had a question regarding that too. Does Weber's force law goes in contradiction to that model? Because in my mind, the structured atomic model is very mechanically static, if I can say
static
that.
electricity idea.
It's more like a geometric static construction, but Weber would say that it cannot work.
It shouldn't
that
be like
way.
that. Yes, it shouldn't be like that. You're right.
So and at the atomic level, all the particles inside would be constantly moving. Right.
And not only moving, the smaller the faster, and so on and so on and so on.
Right.
So it's a different kind of model, which has not been developed. So we just have, I gave here just some examples. But as I said, nowadays we have a huge knowledge of nuclear physics, but no one ever applied Weber for these. We don't know about the neutron, the proton, what's the difference between a neutron and a hydrogen atom, and so on and so on. So there are many things that we should apply Weber to see if it works or not, if we need extra terms for Weber's law and so on. Probably yes. But you see, people need to work to see what we can remove from Weber's beyond these aspects.
So it's a completely different paradigm.
Quantization and other things and so on.
And I have another question that came to mind also is, does magnetic spin has anything to do with this?
Yes, totally, because and even I believe, for instance, that we know that the electron has spin. To me, it must be rotation, or two particles orbiting around one another, but it must be related to rotation and spin. Also, the textbook states it's not. But
because I remember from my courses in college, they were calling it spin, but they were very adamant in saying
yes, they say it's not. But in my mind, it must be. It must be. So. So maybe we have, for instance, quantization is related with this spin of the particles inside the nucleus and the spin of the elliptical orbits around the nucleus, if they have multiples of one another or submultiples, so that we have some kind of, as Matthew said, Ehret said, this harmonic of Kepler and so on, this motion inside the nucleus and this motion out in the orbits outside, if they combine in harmonic frequencies, so we might have these quantizations. I don't know, but possibilities, they are there. So maybe these might lead to these quantizations. I remember that Weber and Zollner and others at the end of the 19th century, when they began to see these spectra of the atoms and so on, so they look at these two possibilities. The structure of the atom might explain this spectra of light, and the opposite. If we know the spectra of light, that might help us to model inside the nuclei, inside the atoms. So they look at both ways. And also this Weber and Zollner, as you said, Kevin, that inside this critical distance, Weber has a very beautiful quotation. He said that they live in a world of themselves, the particles inside the nucleus, because we need to have a huge energy to break that, you see. But they were even thinking about this possibility of splitting the nucleus qualitatively. But you see, the idea was there. And not only that, breaking electromagnetically with electrodynamics, you see. And we nowadays know that this is possible with this nuclear reaction and so on and so on. But they were always already predicting these kind of phenomena, which to me is just fascinating. To me, it cannot be a coincidence that when we plug in 2 positrons, you get 10 to minus 15 meters, which we know it's the right size of the nucleus. To me, it's too much to be just a coincidence. So many things is there. The laws of Faraday, Ampere, telegraph equation, wave equation, and so on, and conservation of momentum, energy, the model before all of these experiments by Rutherford, Balmer, even before knowing about the electron. Weber was the first to say that a particle should have a mass and a charge. And he even said that when they didn't know about what was a current and so on. Weber initially thought that a current was positive and negative charge moving relative to the wire in opposite direction with equal and opposite velocities. Later on, Weber himself began to speak of the current as only one kind of charge moving. For instance, the positive fixed in the lattice like nowadays, and only the electrons moving relative to the wire. Weber was speculating that much before we knew that only one kind of charge moving. Moreover, Weber, in all of these planetary models and so on, he said the positive and negative charge have equal and opposite amounts of charge, Q plus Q and minus Q. But the masses, he said, they should be different. As we know, for instance, the proton is 1,800 times heavier than the electron. Weber was already predicting that. It's just fascinating. Everything published in 1870s, much before the electron, much before the proton, much before everything. It is just fantastic, everything. Too many positive things to be true, but it is there.
Yeah, there's also
for anyone who wishes to read, just it is there, published.
And you mentioned also, because one thing that I look for in in the laws of nature is beauty, right, and simplicity. And
Yes.
one thing that I find very attractive about Weber's law is, you mentioned it, the fact that you find Coulomb's law, Faraday's law, and Ampere's law inside of it, depending on the values of R dot and the
Yes.
second and first derivative of R.
And
So
you see,
this is very...
if you see Weber, if you read all his papers, he was a fascinating experimentalist. He was not a theoretician. Everything which Maxwell praised on Weber was the quality of his high precision, which Gauss and Weber introduced in electrodynamics. And Maxwell said, no one before had obtained things with such a high precision. For instance, this magnitude C, which Weber introduced in 1846, I'm slide 6 now. So Weber introduced this constant, which has to do with the relation between Coulomb's law and Ampere's force between current elements, epsilon naught and mu naught, okay? He wants to unify them, so it appears a constant. So Weber introduced this constant, which nowadays we call 1 over square root of mu naught epsilon naught in the International System of Units. So this was introduced by Weber, also not with the International System of Units, but with Weber and Gauss' absolute system of units. But this constant was introduced by Weber. The first one to measure this constant, the first one in history, was Weber and Kohlrausch in 1855, 1856. They obtained, I won't go into the details here, what was the meaning of the C for Weber and so on, but they obtained this 3 times 10 to 8 meters per second. So they said, and Kirchhoff, soon after, 1 year later, obtained the telegraph equation, the wave equation. And Kirchhoff said explicitly, so that the signal will propagate along the wire with light velocity in vacuum. So to everyone, Riemann, as I don't know if it was Matthew Ehret who said, but Riemann, who was a student of Weber, published a paper. So everyone were impressed by these two results: the measurement of C, which gave the same as light, and the wave equation, which Weber and Kirchhoff obtained in 1857, 7 years before Maxwell obtained the wave equation. So everything saw a connection between optics and electrodynamics. But you see, Maxwell himself made a measurement of this quantity C, which is not a velocity at all. It has to do with two systems of units. The first, when Weber measured this constant, it might have any value. It might be 10 to elevated to 5 meters per second, or 10 elevated to 20 meters per second. It might have any value. No one had not an inkling of the idea that it might have any connection with light.
That's huge.
When we compare the measurement of Weber with the measurement of Maxwell, 10 years after Weber, it was in 1866 when Maxwell repeated the experiment, and compare that with the known value of nowadays, light velocity in vacuum, the value of Weber is 3.6% different from the modern value. And the measurement of Maxwell is 4.5% worse than that of Weber. You see, when Maxwell made this measurement, he knew exactly the order of magnitude from Weber. Moreover, for Maxwell, the constant needed to be light velocity. To Weber, it might have any value. And Weber didn't have no idea of its order of magnitude. But the precision of Weber was better than that of Maxwell, made 10 years later. You see, Weber was an amazing experimentalist. He was not a theoretician. Every time Maxwell praises Weber and Gauss is because of the high precision of their measurement, which no one tried to equal before them. And this is just an example. I can't take the book here, but in my book, there is the last chapter of these 4 volumes of the last chapter of volume 3. There is a section in which I wrote about Weber's constant C, Maxwell constant C, and their relation with light velocity. Then I give the published measurement of Weber, the published measurement of Maxwell, compared with the modern value of light velocity, and you see that the precision of Weber is 3.5 or 3.6% different from the modern, and the Maxwell is 5.6 or 5 worse than that of Weber. Just to give you an idea of, and I quote someone published in 1957, 100 years after this measurement, saying that very few experiments in the history of physics have such a high level of precision, especially when they were measured for the first time. It's just fantastic.
Excellent. Thanks a lot.
How much more time do you have, Professor?
I can continue if you wish.
We have 3 people still on the list.
Okay, let us wait for them.
Okay, let's get through. So the next person who's been waiting for a while is Brian. Brian, are you still there? Brian Kaufman.
Sorry, took me a second. Can you hear me now?
Yes, sir.
Okay. The question I have is about whether or not anyone has done any comparisons of Weber's force to try and derive the electroweak force.
Not that I know of, Brian. So as I said, maybe it's someone, but for the papers I saw, I don't remember it. I remember about this strong nuclear force, but about the emission of electrons by atoms, radioactive atoms, and so on, beta decay, and so on, I didn't see. Maybe there will be, someone has published, I don't know. I'm not aware of. As I said, I hope someone, maybe you, maybe you will begin to try your hands and see what we can get out of this. Who knows?
If it hasn't been done, it sounds like a worthy attempt.
Mhm.
Yes, sure, no doubt. Everything is worth trying to, because we are going in a new field almost. So it is old. It has been stopped. Its development stopped 130 years ago. So we can continue from now on.
Is there? It just surprises me that no one has developed a center to support the development of the the propagation of these ideas. I mean,
yes, but you see, it just happened. History of science goes like that. It is paradigms from time to time. So I like very much Thomas Kuhn's book, The Structure of Scientific Revolutions. I feel that I like it because I feel it in my skin when I face my colleagues, conferences, and so on, the reactions and so on. I feel everything in my skin, how they affect my students and so on, fellowships and so on. And I have been surrounded by relativists and particle physicists my whole life, tried just to survive. It's not easy. I say that I need to kill a lion a day, almost.
A lion or a liar a day.
Really, because you see, I'm a professional physicist and I am working in a university, so it's not at all easy, not at all. But I recommend it because we learn and we met so many different people especially when we go to original ideas like Weber and so on. I appreciate that in the long run. Also, I did suffer a lot during my whole career, but I survived up to now.
Well, you definitely have a humorous nonlinear disposition that I think has allowed you to thrive and survive in that type of hostile environment over the years. So
yes, I did suffer a lot during the first years of my career. Later on, I get used to it, and so I just managed to survive. I could not, maybe. Many didn't survive because the pressure is always so. And we will always be like that. I know that. Even in 2,000 years, when someone comes different ideas and so on, that's part of nature. But in the beginning, I was too idealistic. So I did suffer a lot. Nowadays, I'm used to. So.
Right.
But especially for students, it's always difficult. So I try to alert them and so what they might receive and what. Well, but everything is worth trying. So if you try your hands, I believe, even if you don't believe, just try it and see what you get. Maybe you'll find gold.
Right. Your students are very lucky. Kelly has been waiting for a while. Kelly, are you still there?
I'm still here. Professor Assis. Yeah, you just described yourself as a professional physicist, and here I am. I always describe myself as a closet physicist who's just coming out of the closet.
Okay.
But yeah, I have a regular working life, but like it's always since for a long time I've always just in my spare time I would just study. Just pure physics, I guess, just by myself. I'm not very proficient in mathematics very well, but I have an imagination. You were already talking about my question where you're discussing Weber's constant, he, I guess he came up with this idea of the constant, like the speed of light, I guess, but in his view, it wasn't. Could have been anything.
Yes.
And he actually did experiments to get that number. And then I've read a little bit about Maxwell. I could never understand his whatever his equations were. They're just way too high for me.
Yes.
You mentioned he discovered, he did experiments that he measured the speed of light.
No. He didn't measure the speed of light. He did measure an electrodynamic constant, which relates Coulomb's law with Ampere's force law. The experiment was like that. He did charge two spheres, and then with a torsion balance, he and Hirsch in 1855-56, they did measure the force between these two spheres with a Coulomb torsion balance. So he could know the amount of charge that were in these two spheres. Then he did, I will simplify it here, okay? Then they did discharge one of these spheres very fast. When this current discharge, they by a wire with in water and so on and so on and so on, there was a current flowing down to the ground, okay? And this current did deflect a magnet. And so they could, by the amount of the deflection of the magnet, they could know the amount of current which discharge, okay?
Yeah.
Because the deflection is proportional to the amount of current. As a matter of fact, it was a very fast current, so they could even know the amount of charge that was discharged here, the integral of current over time by the impulse it did give to this magnetic needle. And so he, in the international system of units, when he did measure the force between the charge, he could measure, let's say, the epsilon naught. By the discharge, he could measure the mu naught of Coulomb's of Ampere's law. And then he could obtain this constant here, which relates electrostatics with Ampere's force. And then he did obtain a purely electrodynamic constant. They didn't measure the velocity of anything. But then they showed that this constant, which had the unit of a velocity, the value, the numerical value of this constant, from this equation, just from this equation on slide 6, the first line of this equation, we know that C must have the units of a velocity because it is 1 in the parentheses, 1 minus r dot square over 2c square. So the C must have the unit of velocity, meters per second. Okay.
So,
but they didn't, it was not an optical experiment. They didn't measure the velocity of a particle or of light or anything. They measured two forces, force between two electrified charges, a torsion balance, and the torque on a magnetized needle when one of these charge was discharged. And from these two measurements, they could know the ratio between electrostatics and electrodynamics, something like that. And it comes out to be exactly the same as light velocity in vacuum. When this result was found, it was clear to everyone, specifically Kirchhoff wrote specifically in his paper, 1857, that the signal propagates with the same velocity as light in vacuum. A signal along a wire, like a telegraph signal. You have a wire, then you make a perturbation here, like you approach and move a magnet close to an extremity, then a signal will propagate along the wire. And Kirchhoff obtains theoretically from Weber's law that it would be wave equation with the same C which appears in Weber's law. And
So
then
it just happened to be the same, like, but
happened to be the same.
so
And
he calculated that just through simple mathematics.
yes, Weber made the measurement. Then next year, Kirchhoff and Weber also, they did make mathematics, a signal propagating along a wire, like a telegraph. And they obtained a wave equation with the same constant which appears in Weber's force law, which Weber had just measured. And so to everyone, it was clear now that optics and electrodynamics was quantitatively connected. So unification must be there.
And that led me to like just wondering, you know, the speed or this constant, and then it just makes you wonder about like the existence of the ether, and you know they had tried to prove it but they never proved it, and I guess they still haven't. And I guess my other question is, what do you think? Do you think there's an ether or not?
I'm not sure, sincerely, Kelly. I am sympathetic to the idea that, but if there is an ether, in my mind, it would be just like Weber. It would not be a continuum or a field or things like that. It would be just like a plasma, many electrified particles moving around in space and so on. And light might be a signal propagating in this medium, just like a telegraph signal propagating along a wire. We have many particles.
And everything else would be just nothingness, I guess.
Yes. In my mind, but I don't know.
All right, well, that's a valued opinion.
Certainly, this was the kind of ether that Weber did have in mind. Weber was always an atomist. He was not a continuum. He did always believe in atoms and things like that. And so even his ether, which he did believe, would be composed of many particles, electrified particles, moving around and so on.
Interesting. Thank you.
Monty.
Thank you, Professor. Very insightful, and my greetings from Baja, Mexico.
Okay.
This phenomena of, the MEMAC, the military-industrial media academic complex, never ceases to amaze me on how they revise history, manipulate history, intervene psychologically on the mass consciousness. And in light of that, I spend a lot of time on the web intervening in various sectors. And there's two phenomena that I'm witnessing right now. I'm wondering if you could comment. And the first one is there's this new age movement now. Given all the chaos in the world, the fear, the anxiety, people are grasping for something. And I've noticed this new phenomena that's reared its ugly head again, whereas they're attempting to take Vernadsky's work on the noosphere, which appears to be electromagnetic phenomena, given his onion experiments and so forth.
Those Gurvich's.
Yeah, pardon me?
You're thinking of Gurvich with the onion experiments on
okay, well, I'm sorry. But in any case, with Vernadsky on the noosphere, they're attempting to show the noosphere is derived, if you Google it, they're attributing it to Teilhard de Chardin, this mystic primordial force that arises, and completely contrary to the validity of that. Do you have any comments or insight into the noosphere as an electromagnetic phenomena and the work of Vernadsky?
Well, I know very little about the work of Vernadsky. I read something about the words in collision. I believe he has a book with this title.
That's Velikovsky. That's a similar
another person.
Guy.
So I don't know. But even this Velikovsky, I know very little. Just this book and so. And this other Vernadsky, I don't know who is this person. But I believe that most of the phenomena in the cosmos, they are related with electrodynamics. Sure. because the electrodynamic force is 10 to 40 times greater than the gravitational force. So normally we try to think everything in terms of gravitation in cosmology, but I believe electrodynamics is so much more powerful. And so I believe many phenomena in electrodynamics will be clarified when we have more like this electric universe model and so on. But we need to see the details. But
okay, the other phenomena that's rearing its head these days is this whole mythical thing about space aliens. And given that there was a lot of things covered up, the Operation Paperclip, where different Nazis were brought into the country and different things were kept at Area 51 and the DARPA project. Do you have any comment or insight into the potential for actual development of levitation craft using gravity, anti-gravity? Is that a potential insofar as what you see in given your insight into physics?
Yes, the potential is there, but I believe even greater than that is the potential with electrodynamics, you see, because you can have a negative effective inertial mass. So that is just phenomenal. And just like two charges of the same sign attracting one another instead of repelling and so on. So to me, this is already fantastic and great. As regards cosmology, I myself, I don't believe in the Big Bang, in the expansion of the universe. To me, the universe is infinite in space, infinite in time, has always existed. I hope it will always exist in the future as well. But to me, it always existed. And I believe Hubble also was skeptical about the explanation of redshift based on Doppler. Also, he made that in his first paper, 1949. But later on, he began to doubt this, and he believed there was another mechanism responsible for the redshift. And I believe that as well. To me, the redshift, the cosmological redshift, has another origin. It's not to do with motion. And so to me, the universe has always existed, and there is infinite galaxies, infinite suns, and to me there is infinite life in the whole universe. So when they find an alien, I won't be surprised. To me, there should be life in many places. So
one brief follow-up, Professor. Is there any potential that you see insofar as something faster than the speed of light?
To me, that might exist as well. I don't see a problem. No, until now, no one found it. But I'm not funny. People say, "Oh, relativity prohibits that." To me, if they find, okay, Weber does not prohibit anything, so they can find it in the future. I won't be surprised if they do find it. So up to now, they didn't find. But to me, if they find one day, that will be fine. I won't be unhappy or surprised with that.
Yeah, it's never a great idea to impose limits on what we can discover and know in the future, right?
And when a theory makes limits, maybe the theory is wrong, and so one day we can have a different theory, and so.
Absolutely. So Kevin and John Place both have some parting thoughts, some final couple of questions. So I'm gonna splice them in. Kevin, go ahead with your last follow-up question, and then we'll leave it to John to close it out.
Right. Thank you. So I want to come back to this idea that some of the fundamental forces can be done away with. And you've mentioned the idea that the electric force plays a much bigger role in the universe, which I tend to lean towards. I wanted to ask you about the late Wallace Thornhill theory about the gravitational force being a dipolar force inside the nucleus Can you comment on that? What do you think about his idea?
Yes, if you see, let me take it here just a moment. Oh, no, it's not here, but if you see, oh, it's here. If you see the volume 4 of these collected works of Weber, the subtitle of volume 4 is Conservation of Energy, Weber's Planetary Model of the Atom, and the Unification of Electromagnetism and Gravitation. Weber himself, in his last major memoir on electrodynamic measurements, which was published only posthumously in 1843, at the end of the 19th century, he speculated that gravitation might be due to the attraction between positive and negative charge being slightly larger than the repulsion of charge of the same sign. So if we have many two neutral groups of particles, there would remain a very tiny force of attraction between them. Also, they were two neutral groups. So he tried to explain gravitation being due to these very residual forces, that the attraction between positive and negative would be slightly larger than the repulsion of charge of the same sign. That is one possibility of finding the unification between electromagnetism and gravitation. Weber tried. I myself, in 2 of my papers, I did go in your idea, Kevin. I assume that the force between positive and negative was the same as between charge of the same sign, but I showed that if we have oscillating dipoles, that there would be also the 2 dipoles would be neutral, electrically neutral, or two groups of dipoles would be electrically neutral. There would remain a residual force order component of the order R dot over C to the force power. Okay, so Weber's force goes until the second order, R dot square over C square. If we have many groups of dipoles, that cancels to 0. But if we suppose that Weber is only an approximation and that we might have force orders, 6 orders, and so on, then we can show that dipoles, there will be a net attraction between 2 neutral oscillating dipoles in all directions. There will be a very tiny force order of attraction, which might be what we call gravitation.
Which would kind of explain also the difference in order of magnitude between the electromagnetic force
and so
the
this
gravitational
somehow
force.
is related to this idea of the late Walt Thornhill. He invited me. I did go to a conference with him in England in 2019 on the electric universe. He was kind enough to invite me, and I did go there, and I did make this kind of presentation there. You can see on my homepage, there are 2 talks which I gave in 2019 in the electric universe. One was on Weber's electrodynamics, just like this one, and another one was on relational mechanics, which is based on Weber's law applied to gravitation and the implementation of the Leibniz and Mach's ideas about the origin of inertia. But your idea, Kevin, I believe it's very promising, that gravitation might be due to this residual force of oscillating dipoles of electrodynamic origin. Okay, so I have 2 papers on this connection, but they need to be developed. They are just the first steps.
Sure. Well, count me in on buying your books. You got to be very intrigued, for sure.
Okay.
Cool.
Thanks a lot.
All right, let's let's pass it over to John Place to round out today's seminar. John, are you still there?
I'm still here, yes. With respect to the erasing of continental contributions to physics, and specifically German, there's one specific aspect with respect to why William Thomson, later Lord Kelvin, would have wanted to erase Weber. Because the first telegraph was the Gauss-Weber telegraph, 1833.
Yes.
But the patents for the telegraph in the English-speaking world, there are two of them, one in England and one in the US, they date to 1837. So and of course, Lord Kelvin was knighted for the organization of the first transatlantic telegraph cable.
Yes.
So he had a very personal investment in erasing Weber, not just a general English tradition of trying to erase continental contributions. That's the first comment. Second comment, a few years ago, I took my family to visit some German cities. And one of the highlights of the visit was going to Göttingen,
Yes.
to pay our respects to the statue where Gauss and Weber are discoursing.
Yes.
Yeah. Now you mentioned the wall Thornhill.
Yes.
I had the privilege of meeting him 3 times in my life. I lived for 15 years in Australia, so I met him originally there. You published in Portuguese, that's how I learned to read Portuguese, in 2013, your Relational Mechanics. And then in 2014, the English book arrived. And I met Wal Thornhill at the Electrical Universe conference in Albuquerque in 2014. And I asked him, what do you think of Andre Assis's work? Well, I think he deserves a Nobel Prize for his contribution. So Wal Thornhill had a very high opinion of your work. Thornhill had a certain suggestion that quantum effects might correspond to information which is passed very fast through longitudinal waves in the ether. That's one possible question, if you choose to answer it. And the second is, does the Weber model give us any idea about how plasmas work or how plasmas develop with all the boundary layers and so on and so forth?
Okay, I will try to make some comments on Kelly and you, John. As regards longitudinal forces, yes, there is this possibility with not only Weber, but also Ampere. As I said, 2 elements pointing along the same direction, along the straight line connecting them, according to Ampere, should repel one another. This force should not be there according to what we learn in the textbooks. So many experiments are being doing related to these longitudinal forces. But if we go to Weber, it's also longitudinal because current elements are charged in motion. So the force of Weber is always along the straight line connecting them. So we have this possibility. Wal Thornhill I just met him personally in 2019 for the first time, but we did have some exchange of emails before, and I always respect very much his work, his open-mindedness, and after we met even more, because he always gave me a lot of support. So it's a great pity that he passed away so early, but he left his very important contribution to the electric universe, which will be a lasting one. But also you and Kelly mentioned, it's a very important that Kelvin was really ignited, became Lord Kelvin because of the transatlantic telegraph, 1857 or so. And he also obtained the wave equation, but without the self-inductance. So he didn't obtain the wave equation. he obtained a partial telegraph equation. Only Weber and Kirchhoff did obtain the complete telegraph equation by taking into account self-inductance and from Weber's electrodynamics. So in 1857, they did obtain the first time the wave telegraph equation. When resistance is negligible, it goes back to the wave equation. But you mentioned correctly that Weber and Gauss, they did create the first working telegraph. 1833, 24 years before Weber himself did obtain the first time the wave equation. But the first working telegraph was built by Weber in his hands, and it was a 2 kilometers line from the Institute of Physics in Göttingen until the Sternwarte, the observatorium where Gauss worked in Göttingen. And I learned my German in 2001 in Göttingen at Goethe Institute. I did spend 4 months there. It was just fascinating. The Goethe Institute, where I did go, was where Weber and Gauss spent most of their careers. But when we go to visit, I also saw this Gauss-Weber Denkmal, the statue of Gauss and Weber. And originally, there was a telegraph line in the hands of Weber, which was lost during the years. But when we go to the observatorium in Göttingen, the only commemorative plaque that is there, it's not related to the mathematics of Gauss, nor of any astronomical discovery like the calculation of the orbit of Ceres, nothing of this kind. The only plaque that which is there in the observatorium in Göttingen is the 1833 invention of the electric telegraph. So it's very nice. But the England, they didn't want the Kelvin and so on, transatlantic. So even the telegraph, they seems to be due to the English people, but it's not so. It was due to 24 years before by Weber himself. And Gauss said in his letter that it was everything built by Weber. Weber was then 31 years old, had just been became professor by the recommendation of Gauss at in 1831 in Göttingen. Gauss, the recommendation, became professor, and then a very close collaboration with Gauss. The first result was the telegraph, working telegraph. They did send signals to one another. Later on, it was electric discharge and breakdown. But it's, thank you for bringing this.
Quick, I have a quick question on that note. Did Joseph Henry or Samuel F.B. Morse give credit to the Gauss-Weber work on the telegraph, or did they not?
I don't know, but what I know is that originally it was a twin line. They have a battery here and an induction there. It did work by Faraday's law of induction, which had just been discovered in 1831 by Faraday. And then Gauss and Weber utilized this Faraday's law of induction to make a working telegraph. It was a twin line, 2 kilometers from the Physics Institute to the observatorium. Later on, I forget the name of the guy, but it was a German guy who was accidentally trying to make a telegraph along the railway stations in Germany. And he did notice that the ground works as a return path for the signal. So you could have a single wire and the ground. So it cut the costs of telegraph by half. But he was working in the Gauss-Weber tradition. I forgot the name of this guy. So in the beginning of the telegraph, it was all based on Gauss and Weber, even this discovery. So
fascinating. John, did you have a last thought, or should we?
No, just once more, thank all of you once more for your attention, patience, and please bring these ideas of Weber to your colleagues, to your students, to anyone. So bring that back to life again. I'm trying this for my whole life with very few success. If you help me, maybe we can reach more minds around.
Well, I think that that's a wonderful challenge to put out there. And that includes anybody listening right now on Rumble and BitChute and YouTube in the future who are listening to this. Consider this a challenge. And every mind does matter. You know, at the end of the day, Gauss and Weber themselves were not from some high elite bloodline. And that's why they're geniuses. They were regular people who simply discovered early on a love of truth. And they pursued it in a very, very healthy passion. So anybody can have that fire awoken, and who knows who the next Weber will be in the students around us, or even older students who might discover their little young Weber in their 70s or 80s even. So we'll definitely make sure all of your translations and works are available in the description box, and I encourage everyone to spread them as far and wide as possible.
You can put the PDF of this presentation there as well if you wish.
Okay, I'll do that too. Great. So thank you so much, Professor Assis, and thank you, everybody.
Thank you, everybody. Thank you, Assis.
Thank you so much.
Yep.
Thank you, Professor.
I'm going to research this stuff. Yeah.
Thank you.
Thank you
Thank you, Professor.
Thank you.
Thank you. Thank you so
Muito
much.
obrigado.
Yeah.